In this session, I'm going to talk about co-integration. What does it mean with respect to the time series analysis? And as an application of the co-integration, I'm going to take up a financial application which is cross-hedging, where I have to do a hedging of the risk associated with one financial instrument using another, probably the futures of some other kind of a security. Definition wise, I'm not going in depth in this session, because here the context is how do I really use R for all these kind of purposes. First thing, when I talk about co-integration, the major intention is I want to get to a linear combination. Right, my intention is to create a linear combination between a non-stationary kind of a time series. For a non-stationary time series, right, that particular time series whose mean, variance and other statistical properties are not constant, I want to have some kind of a linear combination of this particular non-stationary time series, wherein I can really convert it into a stationary time series. That is where I'm using the concept of co-integration. So my objective is to convert a non-stationary time series into a stationary one. So because of that reason, once I am able to do that, I would be able to detect long run relationships between the variables. That is where I'll take the example of cross hedging. We can take the long run relationship between the two non-stationary time series data. If I have a non-stationary time series data 1 and non-stationary time series data 2, I should be able to identify the long run relationships between these two data points. Now, for that, I want to really take an example associated with cross hedging. And the way I want to handle this example is, I have taken a data set which contains the data relating to Sensex mid-cap index. The data for this is collected from somewhere 2003 April to 2016 March. So almost 14 years of data has been collected. 13-14 years of data has been collected. And this particular this is the kind of a, so my portfolio, what I want to really look at is, my portfolio is more or less mimicking this particular index. So my portfolio is moving more or less in the same lines as this particular index. So I really want to hedge this, right? Because there is a lot of volatility in the mid cap index possibly. So I really want to hedge, if not fully, at least a part of my total exposure to this changing mid cap prices. So this is where I want to look at probably the futures market, or for that matter any other market with which or first let me look at the futures market. Let's assume that the mid cap futures is not available on the market, and there is no OTC derivatives contracts that are traded with respect to the Sensex mid cap. So directly I don't have any kind of instruments. So I am trying to look at something relatively traded kind of a contract, and for that time being, let's say I have narrowed down on using the Sensex to hedge this particular exposure. So mid cap exposure, I wanted to hedge through the Sensex. So I really want to find out what is the optimal hedge ratio, which means how many units of Sensex do I really need to go short on or long on if at all I want to hedge one single unit of the mid cap futures. So this is what I am calling as the optimal hedge ratio. So this optimal hedge ratio, initially we'll look at a classical approach. So when I am saying classical approach, I'll look at short-term fluctuation. My focus is on short-term fluctuations of both the mid-cap prices and the Sensex prices. The item that I'm going to hedge and the asset with which I'm going to hedge my asset. So the asset to be hedged and the asset with which I'm going to hedge. So both the things, I look at the short-term fluctuations of the prices between both of them. So that is the first approach, which is what we are calling as the classical approach. And after that, we can also look at the long run stable relationship between both the prices so that we can improve the hedge ratio. So this is what is a two-step process as a part of the hedging process. Initially, we are looking at a short term, how the short term prices are fluctuating, differences in the prices. Then we are looking at long term stable relationship between both the prices. Now let's try to look at that particular aspect using R. Here, for doing this activity, I want to use one package which is built in as a part of R, which is called as Arca package. So basically this is having lots and lots of functions, especially to do with the co-integration. Wherever I would like to use co-integration, wherein I am looking at two different time series which are non-stationary kind of nature. So that is where co-integration comes into picture, and wherever I want to use the co-integration as a concept, it's better that I rely on the Arca package. So I'll try to install the Arca package as well along with the Zoo package. So I think R is already opened here. So let me install the package. I'll install the package named Arca. URCA. Alright, I'm installing this particular package called Arca. Yes. Okay, this particular package is installed. So I'll load both I'll load both the Zoo package which has already been installed earlier, and I'll also be loading Arca package now. I have already installed it, so we are loading even the Arca package. So both these things are being loaded. Now we need to get the price data. For that I have maintained it in an Excel sheet. I have the mid cap data right from 2003 April till 2016 March. Similarly, I want to hedge that using the Sensex. So if actually I should hedge it using Sensex futures, but yeah, as an assumption, let's take these are the Sensex futures itself, right? In reality, they are the Sensex values. But for our understanding purpose or for the purpose of using this in R, let's call this column as the Sensex futures itself. So this is the kind of a data. So my portfolio is more or less replicating this. I want to hedge the risk of this particular portfolio using these particular futures. So that is how I want to look at my problem. So let me bring this data into R. So for this I'll call some prices or some index values, right? Let me call it as index. Let me just simply call it as ind_val, which is the index values, right? And we have already dealt with read.zoom, which is more talking about reading a time series data. Now, where is my file? In my E drive. R data is the name of the folder, and this file name is called as sensexmidcap.csv. So sensexmidcap.csv, right? So this is the name of the file that I am loading. Now, because it's a CSV file, obviously my separator is going to be a comma. We have seen that the headings are there in the first row, so that's where we are calling header equal to true. And now the date, this is a monthly data. So that's where we'll say a fun argument, which is talking about the format of the function. So we have dealt it even in our earlier video, where I'll call it as yearmon, which is it will be treating the data as year and month. The format of the data in our Excel file or CSV file is a full year slash the month number. So full year is typically mentioned with percentage Y slash the month number is with percentage M. So these are the various things I'm loading as a part of my ind_val. So ind_val typically contains the data. So let's check what this ind_val typically contains now. So these are the data that are present as a part of ind_val. These are the months, April 2003, because we have given the format as yearmon. This is how the format is going to come out. So April 2003, May 2003, and so on. These are the midcap values. These are the Sensex values. Now, the first part we have already talked about as a part of the hedging. The first part is the classical approach, where I am looking at only the short-term behavior, where I am looking primarily from the perspective of the changes in the monthly prices of both the asset to be hedged and the instrument that is being used to hedge this particular asset. And based on that, we are deriving the minimum variance hedge ratio, or which is what is called as the optimal hedge ratio. So for the short term purposes, we are only looking at the changes in the monthly prices for both the spot price as well as the futures with which we are going to hedge the spot. And this is where we are fitting a linear model between these two. So we know that the linear model in R is executed through a function called lm. So that is what we are going to talk about. So this particular linear model will talk about the changes in your mid-cap prices, how much of changes in the mid-cap prices are explained by the changes in the Sensex values. So to what extent the changes of this are explained by this. So this will become my dependent variable, this will become my independent variable. And whatever the beta that comes out through this particular approach, that is what we can consider as the optimal hedge ratio. So let's try looking at the optimal hedge ratio in this case. Right, I'll look at the differences in the prices. So let me take probably we'll talk about a very simple model, simple underscore mod or simple model. We can simply take it, wherein I want to take the linear model. So in the linear model, my first variable is my dependent variable. What is my dependent variable? I want to take the differences in the prices, right? Mid cap prices. So what is my variable? Indval is the variable, and for that particular indval I want to take the mid cap value. So the difference in the mid cap values is my dependent variable. I'll put a tilde sign, and I'll also put my independent variable, which is nothing but difference of the indval is the name of my data file, and in that I'm considering sensex. So this is my independent variable, and I could very well give whether I want to include the intercept as a part of my regression model or not. If I want to include the intercept, I can close this here. But if I don't want the intercept coming as a part of my regression model, I can very well say plus 0. So when I'm doing a plus 0 in my linear model, it means that I don't want to include the intercept. So I want to set the intercept term directly to 0. So this particular model, right, I got a simple model. So it is estimating the coefficients wherein I am looking at a best fit relationship between the mid cap change in prices versus a sensex change in values over a period. So we can simply look at the summary associated with the simple mod. Right, let's see what this result has come out. Wow. Now you could see that there is a linear model applied where we are talking of the formula is the difference of the individual mid cap values versus the difference of the individual's ind values sensex. These are the residuals in the process, right? The minimum residual is minus 899, the maximum is plus 842. The coefficients are coming out to be something like this. The difference individual sensex, the estimate is around 0.42. Standard error is around 0.01, and which is resulting in a probability value which is the p-value of less than 0.05. P-value is q into 10 to the power of minus 16. So the p-value is much less than 0.05. So which actually tells that the independent variable is significant. Independent variable is significant in terms of determining your dependent variable, and whatever is the coefficient that has come out, that is what is the beta, and beta is nothing but the optimal hedge ratio here, right? So we have got the data out here. So we got a hedge ratio in this example. So we can very well say, if I am looking at only the short term changes, short term price changes, the hedge ratio is, optimal hedge ratio is 0.4257. So to hedge 1 unit of mid cap, we require 0.4257 units of the sensex. So we need to take a position in 0.4257 units of sensex to hedge the risk that is involved in 1 unit of the mid cap. And you could see that the standard error in this case is only 0.0189. Obviously the cross hedge is not perfect. If it is perfect, even I would have got a 1 here. So which means the portfolio, even after the hedging of the portfolio, there is some level of risk that is inherent. To some extent I can reduce my risk, but it is not completely eliminated. So to some extent risk still lies in this portfolio. So my next objective is there any way I can improve on this hedge ratio? And this is where we can look at the long-term relationship, right? So till now I have not used anything to do with the co-integration or any of the stuff, right? So the co-integration, to use the co-integration only, I have actually loaded the ARCA package. And co-integration is more and more useful when I have to look at the non-stationary behavior between the two time series. This is where the opportunity comes. So I am looking at, I want to improve this hedge ratio. So this is where I am looking at a long-term relationship between the levels, both of the mid cap as well as the Sensex, right? So basically what I can look at is I can do the plotting of both of them just to really see how both of them are really moving. So first let me look at my portfolio, which is the mid cap. I'll take a plot, right? I'll take a plot of my particular portfolio. So I'll say Indval hyphen mid cap or dollar mid cap. That is my particular portfolio's performance because my portfolio is mimicking the index. So I am trying to plot for that particular data, right? And I can very well put a heading saying mid cap. So I'll put a kind of, right, mid cap versus Sensex performance. Okay, so this is the kind of heading let's put, and probably on the x-axis we can put a label as date, and on the y-axis we can put the values as index, right, the index values. All right, let's try out. So there is a kind of a plot that is coming for the mid cap. Now to this I want to add my Sensex line. So because I want to add a line to this, I am using the function called line, wherein I am looking at Indval dollar, my particular, whatever is the hedging. So Sensex is the field that I am using for the hedging purpose. So the name of the data file and dollar and the column heading. Probably if required we'll use a different color. Let's say let me use column color is red, and if required we can also use a different line type. So let's put a line type as 2. Okay, some kind of a dotted line is coming out, and this is how the values associated with X are typically moving. Right? We could even set the while limit to make the graph more interesting. So what can very well happen is when we are plotting the y itself, I'll add one more aspect here wherein I'll say y limit. Will change the y limit probably from 2000, no, probably we can change the y limit from 900 to 30,000. We'll set the y limits from 900 to 30,000. So that's the reason this has come in this way, and we'll add the lines to it. So the Sensex is coming in this way. So this is the way the Sensex is moving, and the black one is showing this is the way. So if I have to set my y-axis or something, I can use ylim, and x-axis if I have to set some specific values, I can use xlim. So this is the kind of a graph that is coming out between both of them. Alright, now there is some kind of an upward pattern in both of them. So there is not too much of stationarity being observed in the process, but technically to really come out with whether there is non-stationarity present in the data or not, we can very well use a two-step estimation technique, right? To really check whether your data is stationary or not, I can very well use a two-step estimation technique. So first step is I want to test both my mid cap as well as my Sensex for unit root. Unit root is a test associated with non-stationarity of the data. And for that we actually use, theoretically if you know this, we use what is called as an augmented Dickey-Fuller test. Right? Dickey-Fuller test is actually being used to test whether the series is non-stationary or not. Right? So we'll try to check both of them, both for mid cap as well as for Sensex. We can very well check whether the series is stationary or non-stationary. Right? We can very well test whether our series is a stationary or non-stationary. For this, we use from the ARCA, right? So we'll first test for mid-cap underscore augmented Dickey-Fuller test. That is the name of the variable I am calling. So we have a function called ur.df. From the ARCA package, we are talking of Dickey-Fuller test. So that is what we are calling as ur.df. So I am looking at indval slash dollar midcap. So I am typically looking at the midcap values, wherein the type, right? Once you type the help, you will know what are the variables, what are the values that you can give. We are looking at with drift. With drift is there is a kind of a constant growth that is happening. The average increase in the values that are coming over a period. So we are looking at applying a Dickey-Fuller test on the mid cap prices. Similarly, I can apply it on the Sensex values as well. Okay, so this is what we got when we did it on mid cap. Similarly, I can very well do it on Sensex as well. So let me run even the Sensex one also. Sensex underscore ADF. So I could simply take individual and I'll take Sensex here. So both of them, the augmented Dickey-Fuller test for the unit root testing is typically initiated. So let's look at the summary of both of them. So let me start with the summary associated with midcap underscore ADF. Okay, so these are some of the results that came out using this Dickey-Fuller test. Right, we could see that the regression drift, because we have given the drift as the type. So we are testing it. The formula is I'm looking at the Z difference versus Z lag 1. The difference in the Z values versus the Z value of the previous period and the Z difference of the previous period. So I am looking at the Z value of the previous period as well as the Z difference of the previous period. And the current period's difference is what is being taken as the dependent variable. This is what is an augmented Dickey-Fuller test, including the intercept. So basically there are two variables that we are looking to find out the difference in the Z values of the current period. To find out the difference in the values of the current period, I am taking the actual value of the one period before as one variable and the actual difference associated with the previous period. So basically to model the difference associated with the current period, x2 minus x1 is the current period difference. I am taking it as depending on x1 and also the previous period's difference. The period difference is x2 minus x1. The previous period difference is x1 minus x0. So there is one variable x1, the other variable is x1 minus x0, and I am also including the interceptor. That is what is happening as a part of the augmented decay Fuller test. It's again a regression, but that is what is typically getting performed in an augmented decay Fuller test. So the residuals are, minimum residual is this much, maximum is this much. So this is an analysis of the residual. Look at the coefficients, right? With respect to lag 1, this is the coefficient minus 0.02, and with respect to the difference of the lag 1, it is the coefficient is 0.11. Now, what is, look at the p values. 1 with respect to lag 1 and even the difference with respect to lag 1. The p values, both of them are greater than 0.05. Both the p values associated with this augmented decay Fuller test, right, they are greater than 0.05. So obviously we know that the null hypothesis cannot be rejected, right? The null hypothesis cannot be rejected. And what is the null hypothesis? The augmented decay Fuller talks about the null hypothesis is associated with non-stationarity. The null hypothesis is associated with non-stationarity. I cannot reject the null hypothesis, right? I cannot reject the null hypothesis. So which means I can very well assume that the mid-cap values are not stationary. I'm very clearly getting a statistical test saying that the mid-cap values are not stationary. Basically, I am looking at the dependence on the previous period's value. The difference between the current and the previous period, depending on the previous period value, is a major assumption associated with the non-stationarity. And here it is very clearly saying that there is not much of a dependency with respect to the previous period value, which means there is a possibility of non-stationarity very much present in the data. The same logic I can test it with respect to Sensex as well. So I'll say summary of what is that variable that we have used, sensex underscore ADF. So let me call it as sensex underscore ADF. Even in this case, the p value is greater than 0.05. The p value associated with the lag is greater than 0.05, so I cannot reject the null hypothesis. And here the null hypothesis is associated with non-stationarity of the data. So the null hypothesis associated with non-stationarity cannot be rejected, which means both the mid-cap values as well as the Sensex values, both of them are non-stationary in nature. This is a very interesting observation from the data. Both of them are non-stationary. This is where the cointegration comes in more and more handy. Now that we came to know that both of them are non-stationary, so we are trying to look at the static equilibrium between both of them and basically test the residuals that are coming out for the stationary time series. We are going to test the residuals that are coming out for a stationary time series, and even that we are doing through an augmented decay Fuller test itself. So which means I am primarily looking at finding out not the differences. I am primarily looking at finding out the relationship between the prices itself, between the original values itself now. So I am going to take an LM, right? Probably let me do, I want to do a modified model wherein I want to take the linear model. Now it's not between the changes in the prices of both of them. I'm actually looking at the prices of both of them. So I'm directly taking mid cap as my dependent variable. Tilde sign, I am considering the Sensex as my independent variable. So I'm directly taking this particular part. So my mod underscore model is coming out to be this, for which I'm going to store the summary for the same. So I'll call it as summary underscore mod underscore model. This I am going to store the summary associated with mod underscore model. So whatever came through the mod underscore model, I am taking the summary of the same. So if I am looking at what is the summary that is coming out, I'll go with summary underscore model, which is showing that this is the intercept, this is the individual Sensex value, the p value is less than 0.05, and I also have, these are the different standard errors that are coming out, and there are some amount of residuals that are coming up. So this is what I really want to store now. If we have looked at the mechanism, we said that first I'll find a static equilibrium, and after that I'll do the testing of the residual. So I have to capture the residual. I'll use a variable called error, where I'll be capturing the residuals associated with my summary. Whatever is the summary that I have got, right? What are the residuals that are associated with the summary is what I'm going to capture. So if you look at my error term, it contains for each of the things what are the residuals that have typically come out. And now I will be performing the augmented Dickey-Fuller test on the residual values. I will not perform it on the original data. I am performing the augmented Dickey-Fuller test on the residual values, which means I'll say error underscore augmented Dickey-Fuller if I want to really find out. So I'm using ur.df, which is the function associated with Dickey-Fuller test. So which I would be performing on the error data, and here I'll not be choosing the type as drift, because this is not something that is, the error is not increasing in a particular fashion. So I'm not putting any kind of a type here. So my error is getting plotted as an augmented Dickey-Fuller test. So I can very well look out for the summary that is associated with error underscore ADF. Now this is where you could see a very interesting part. Right now now we are actually executed the Dickey-Fuller test on the error term, residuals. I wanted to really look at the stationary time series associated with the residuals. Now this is where we got the test statistic, right? You could very well see what is the p-value here, 0.0522, right? We got the test statistic here as 0.0522. Obviously it's slightly greater than 0.05, but to a large extent it is much lesser. So the p-value here is slightly greater than 0.05, but it is almost lesser. Probably it's very much around 0.05. So I can very well reject the null hypothesis just for an understanding. Probably if it has been much lesser than 0.05, it would have been much more better. I could have rejected the null hypothesis of non-stationarity, which means I can very well assume that the residuals are coming out more and more stationary. Right from this, I am able to make out that the residuals are more and more stationary. So if the residuals are more and more stationary, I can very well confirm that both my variables are co-integrated. So how do I really come out with the testing associated with co-integration? First thing is I'm looking out for the unit root test, right? I'm looking out for the unit root test associated with the variable 1 as well as variable 2. That unit root test I'm performing with the drift for both of them, and it should not reject the null hypothesis, which means it should give me that both of them are non-stationary. And after that, I'm trying to fit the model and try to look out for the non-stationarity of the residual. And when I'm trying out the non-stationarity of the residuals, I'm getting a p-value less than 0.05. So I'm able to reject the null hypothesis, wherein I'm concluding that the residuals are more or less stationary. So when I'm getting this kind of a situation, the original data values are non-stationary, and the residuals, after fitting the model, after fitting a linear model between them, the residuals are coming out to be more and more stationary. That is what will lead us to discover that both the variables are co-integrated, and which will give me the second step. The second step associated in co-integration is an error correction model. Right, in the second step, we'll be talking about an error correction model ECM. So basically talking about, which is more and more of a dynamic kind of a model, which typically talks about to at what rate, at what speed the system moves back to the static equilibrium. That is what is being understood by this error correction model. To what extent the values are moved back to your static model, which is what is your summary that has come out with respect to your earlier model that we have fitted for our residuals. So at what speed and how the system moves back to the static equilibrium. For that, we are simply looking at, first of all, two variables. Probably I'll call it as difference in mid-cap prices. So wherein I am taking diff of the Indval dollar mid-cap. I am taking one variable. Difference in the mid-cap prices. Difference in the Sensex values. I am taking one more diff Indval dollar Sensex. So I have taken the difference of both of them. I'll also take the error lag term. What is my error lag term? I'll take the lag value of my error term with a k value equal to -1. We have already applied this. How do I get the lag of one period before? Now this is where we get our modified, or this is where I get the model that is associated with my error correction. In this, we'll try to fit a linear model between here two things. I'm trying to fit a model between the differences associated with my mid cap as the dependent variable, but in the independent variable, along with taking the differences associated with the Sensex value, I'll also take the error that is associated with the previous period. That is what is the improvisation or the error correction that is coming as a part of my model. When there is a co-integration, that is the kind of an error correction that is typically coming up. So now when you look at the summary that is associated with mod underscore ECM, there is a possibility that your hedge ratio is improved. Look at this hedge. So here we got the coefficient as 0.42. So earlier the hedge ratio was around 0.40 or something. Now the hedge ratio has actually become 0.42. There is a slight improvement by considering the non-stationarity of the behavior between both the values. So by considering the presence of a long-term relationship between the mid-cap prices as well as the Sensex prices, we are able to improvise the hedge ratio a little bit, right? So whenever the large deviations are going to come out, right? If you look at the error term, the coefficient that is associated with the error term is a negative small value, but whatever is the coefficient that is associated with the error term, because it is negative, when there is some deviation between the prices, that is going to be corrected. So there is a kind of a long-term stable relationship that is going to come. So basically this is how, when you really find that your data is non-stationary, we try to work out the co-integration process between the data items to really fit in the relationship between the two time series data. So basically when you observe the two time series data exhibiting more and more non-stationarity kind of a behavior, the better way to build the relationship between them is using the co-integration process, and that is what I have demonstrated through the usage of the ARCA package. If you have any further queries regarding the same, you can very well get back to me by giving me a call on the number that I have provided below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.